Okay, guys, sorry about the internet issues. Internet just going on and off. We are back. We are back. So we will still manage our 15 minutes. So let me go back to what we've been saying ever since the beginning of today. Hopefully, no disconnection problem will happen in the next 15 minutes or so. We are discussing the laws of thermodynamics, fundamental laws of thermodynamics. In thermodynamics, we only discuss, in this aspect, we discuss gases. We are not particular about other things like water or solid. However, because water is a fluid, it sometimes can be applied to a fluid. Most of the things we discuss in thermodynamics, when you hear the word thermodynamics, we're talking about specifically gases. Now, we discussed the Zeroth law, saying that these are the four basic laws we are looking at today. The Zeroth law, the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. Like I said, this is mostly a general, the Zeroth law is mostly a general situation. And so the other ones are specific. They are targeted towards one issue or the other. Now, the Zeroth law, where we talked about thermal equilibrium, where if two systems, A and B, is in thermal equilibrium, and also A and C are in thermal equilibrium. It also means that B and C are in thermal equilibrium. So you can play around with any of those three bodies, any of those, the A, B, C. If you note, the sizes of those A, B, C are not the same. They also may not contain the same quantity or the same nature of substances, the same substances. Okay, they may not contain the same substances. Their volume may not be the same. But what we are saying is here that if two systems which are equal in temperature to a third one, that two systems which are equal in temperature to a third one are equal in temperature to each other. Okay, so that is the zeroth law of temperature. It doesn't mean that everything is zero, as the name would want to imply. Now we also went to discuss the first law of thermodynamics, which is that this equation is very important. This equation here very, very important. That the amount of heat given in or removed from a system, the amount of heat supplied or removed from a system is given by the change in the internal energy plus the change in the work done, or plus the work done and the system plus change in work or change or the work done. So we can make any of them the subject of formula, just like we have the equation down there. We have that in this last expression, the U, which is the internal energy, of the system is made the subject of formula. We now have that it's given us the heat minus work done, the quantity of heat minus the work done on the system. Also, we also said that the first law of thermodynamics is similar or is akin or is based on the law of conservation of energy. Usually states that energy can neither be created nor destroyed, but can be converted from one form to the other. Okay, that is, energy can flow from one place to the other. It can change its form from electrical to mechanical or vice versa. So it can change from one form to the other. So the energy supplied to a system will be as a result of the change in the internal energy and the work you are doing on that energy. And we assume that the system is isolated, that is not leaking or something is not being done on it. There's no external influence on the system. Then we went to talk about some equations that can also be used on the first law. Like take for instance now that the internal energy of the system, the change in internal energy of the system can be given as the specific heat capacity at constant volume. Specific heat capacity at constant volume, which is CV times the change in temperature times the change in temperature. So if you can make here we made CV the subject of formula, but du can be given as this form, and then we can rewrite in such a case. We can even rewrite the first law in this format. But like that is just a case scenario. Another way is that we have an expression for the work done with regards to the pressure and the volume of the gas. We are assuming that we have a gas, you are changing the temperature, maybe changing the volume in a piston, in a container. You have a frictionless piston, so you change, maybe you press the piston down, and so you reduce the volume of the gas. It will be giving us the pressure you apply on the piston times the change in the volume. Times the change in the volume. That will be the work done. We can, like I said before, the connectivity issues, that we could also have work done being written in several other equations. So as the other equations with regards to temperature as well, there are other equations. Then we went to talk about the second law of thermodynamics, where I was explaining that if we have, it says that it is impossible, you cannot have a machine that all it will do on its own, you have a machine on its own, you will remove heat from a lower temperature to a source at a higher temperature. Normally, if you stay, you have two bodies, or let's say you get to or a friend of yours that is maybe the body temperature is high, is feeling hot, also you start to see that the heat from your friend will now be transferred to you. Okay, it is impossible to have a machine that all it does to be to remove heat from a low temperature body to a high temperature body. And so that is what we have. When we play around with it, we also have the Carnot circle. We also have the refrigerator circle. As some of you, I don't know your department, you work with other kinds of engines. We have the heat engines, we have the Carnot engine, we have the diesel engine, we have the auto engines. That is at the advanced level of these engines that we'll be talking about at other levels as you grow in the system. The important equation derived from this is that with regards to temperature and entropy, regards to temperature and entropy, that if you make in this equation now, if you were to make the S the subject of formula, if we make the entropy the S the subject of formula, we'll have that the S equals to dq divided by T. Okay, all right, dq divided by T. Yes. So where the S in this case is the entropy. So this is the entropy. The Q is the heat transferred, and T is the temperature. So this like I said, there are different forms of this law with regards to the way it is being stated. We have the Celsius statements, we have other statements, but in this particular case here, you can see there we are stating it with regards to entropy, not even with regards to heat removal. The entropy of an isolated system almost never decreases. Such systems spontaneously evolve towards thermodynamic equilibrium. That is the state of maximum entropy of the system. Okay, so we eventually perpetual motion machines of the second kind are possible, right? In the deep study of this, we are going to look at refrigerator system and the rest of it. Okay, for the third law, there's this my friend that used to talk about something in life. He said it is impossible for you to do something in life. Although in religious circles, we say with God, all things are possible. That is nothing that you cannot attain. You attain. However, in the third law, what we are even trying to say here is that the absolute temperature of zero, that is Kelvin temperature zero, cannot be attained. Cannot attain it. So that is what, like I said, you could have here. We are talking about uh, entropy, entropy, or some is it you can call it the you can write in terms of entropy. You can write in terms of enthalpy, enthalpy, which is the heat. You can okay. Look at it said at zero temperature, the system must be in a state with the maximum thermal energy. Maximum thermal energy. Okay. The uh, issue here is that when we go deeper in the study, we try to look at superconductors. Superconductors. If you observe some of these gas laws, like the Gay-Lussac's law, when it is being drawn, we will have at a certain place we have dash dash dash. That is if you are looking at temperature, maybe versus the pressure, temperature versus pressure on the vertical axis of the temperature. Okay, sorry, on the horizontal axis of the temperature, we are going to see dash 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 getting to zero. A certain region, maybe 0 Kelvin. It is not possible for us to attain such. Now, if we were to attain such, there were some scientists recently that were working on that. I see Korean scientists, and they attained some uh, equations talking about those kind of semiconductors that could be in that format. What we mean is that once you have energy, you will not be able to finish consuming it. Let's say, for instance, now your phone there, you just drop one energy, it will last you. Let's say you charge your battery, it will last you forever. Like just keep lasting. So as at that level of very cold temperature, you could have like a metal will be like will be flowing out, not like liquid, but will be like a gel-like substance that will be flowing out. So it is impossible for us to attain the temperature of zero, Kelvin temperature of zero, Kelvin temperature of zero. So that is the entropy of a system approaches a constant value as the temperature approaches absolute zero. Absolute zero. The absolute zero is of Kelvin temperature. However, in terms of entropy, we can state here that S is given as K B ln omega there, where omega is the number of microstates. Kb is the Boltzmann's constant. That is where we call it a day for now because of our time is up. Our time is up. When we come next time, we'll look at all these thermodynamic processes. They are when we say something is adiabatic, what does it mean? An adiabatic process, no heat, there's no change in heat. Heat energy doesn't enter nor leave a system. Okay, what is an isobaric process? An isobaric process is one that there's no change in the pressure remains constant. Now, okay, and I jumped, what is a cyclic process? A process in which the state of the system at the end is same as the start of the state at the beginning. That is, at the end and at the beginning, is the same. So that's where we have a kind of like a cyclic process. We also have a reversible process, and we also have an irreversible process. We also have an isothermal process. Isothermal, that is a process or a reaction that happens at constant temperature, or we can say is a system where or a process or a reaction that is undertaken under a situation where the temperature remains constant. And we call it a day here. We'll still meet next time. That is this Friday. We should be just to look at one or few things. All right. Have a nice day, please.